I am Raghavan, chemistry faculty from All Force Colleges. I welcome you all for the All Force Chemistry e-learning program. Okay, session 24th. And in the last 23rd session, so we were doing some numericals based on, that is, de Broglie theory and Heisenberg uncertainty principle. So today in this session 24th also, let us continue the same numericals based on de Broglie theory and Heisenberg's uncertainty principle. Okay, now let us note the numerical. Okay, the numerical I will read. The mass of an electron is 9.1 into 10 to the power minus 28 grams. Mass of an electron, that is problem. So problem is mass of an electron is 9.1 into 10 to the power minus 28 grams. Okay, it is given. Mass of the electron is given. The uncertainty in the velocity is equal to, uncertainty in the velocity is equal to 2 into 10 to the power minus 3 centimeters per second. That means delta V is equals to 2 into 10 to the power minus 5. 2 into 10 to the power minus 5 centimeters per second. Centimeters per second. Okay. Calculate the uncertainty in the position of the electron. Calculate uncertainty in the position. That means delta x we have to calculate. Delta x we have to calculate. And options are given in, that is CGS centimeters it is given. Options are given in centimeters. So we have to take the data in CGS units only. Okay. Once again the problem is the mass of the electron is 9.1 into 10 to the power minus 28 grams. Okay. Then the uncertainty in the velocity of the electron is found as 2 into 10 to the power minus 5 centimeters per second. Calculate the uncertainty in the position of the electron. Uncertainty in the velocity is given. Uncertainty in the position is asking us to calculate. Okay, that is the concept of the given problem. Okay, I repeat the problem once again. The mass of the electron is 9.1 into 10 to the power minus 28 grams. Okay. The uncertainty in the velocity of the electron is 2 into 10 to the power minus 5 centimeters per second. What is uncertainty in the position of the electron? Okay, and we can say within brackets, given that Planck's constant value is 6.625 into 10 to the power minus 27 erg seconds. Okay, that is the Planck's constant value. That is understood. Now let us see. Delta x is equals to h by 4 pi m delta v. That is the formula consider. Okay, right. This is equals to, substitute the values. H is equals to, that is 6.625 into 10 to the power minus 27 ergs, minus 27 erg seconds, erg seconds. Erg seconds. Okay, by 4 into 3.14 into mass of the electron given 9.1 into 10 to the power minus 28 grams. It is given in CGS units, grams, into delta V, that is 2 into 10 to the power minus 5 centimeters per second. This is the data available in the problem. Okay, on complete substitution, that is delta x is equals to, so that is 6.625 into 10 to the power minus 27 erg seconds by, okay, on simplifying this, that is 4 into 3.14, that is 228.592 into 10 to the power minus 31 it comes. Yes, 10 to the power minus 31. Okay. So once again be careful, 6.625 into 10 to the power minus 27 earth seconds by, that is the simplification of all this. Okay, that is 228.592 into 10 to the power minus 31. Okay, so this on solving delta x is equals to, on solving this is equals to, that is 0.0289 into 10 to the power. So when it goes, it becomes positive 4. So it is centimeters, or that is equals to, okay, when take the decimal here, that is 2.89 into 10 to the power, 2 zeros get reduced, 2 centimeters. Okay, and delta x is equals to, so delta x is equals to, that is 2.89, so you can make it 2.90 into 10 to the power 2 centimeters. That is the nearest option for the problem. Okay, so please just try to understand the given question. So that is, mass of the electron is given, and the uncertainty in the velocity of the electron is also available. Mass of the electron is given and uncertainty in the velocity of the electron is also given. Based on this, he is asking us to calculate uncertainty in the position of electron. Okay, and remember that, so the formula is delta x is equals to, uncertainty in the position is equals to h by 4 pi m delta v. We know this. Okay, so then h is equals to Planck's constant. It is understood that, see, all the contents are given in CGS units, therefore h must be considered in earth seconds, that is CGS units. Okay, we should not consider 10 to the power minus 34, that is SI unit, joules. Okay, joule second, that is. Now on solving this we are getting, so final answer is this. Okay, that is, it is based on Heisenberg uncertainty principle. Okay, next another problem. Okay, so the concept clearly understood. Okay, data first. Data analysis is very important, first point, and when you are taking the correct right data, then substitution in the problem. Okay, substitution in the problem, then simplification, anybody can solve it. It is not a big problem. Okay, so right. Next problem, let us take the next problem. I read the next problem, listen. Okay, the velocity of an electron with de Broglie's wavelength, the velocity of an electron with de Broglie's wavelength is, that is de Broglie's wavelength 1 into 10 to the power, that is 1 into 10 to the power 2, that nanometers. The velocity of an electron with de Broglie's wavelength 1 into 10 to the power 2 nanometers. So that means wavelength is given, he is asking us to calculate the velocity of the electron. Yes, that is the point. Yes, velocity, he is asking velocity of the electron to be calculated, and de Broglie's wavelength is given. Next, problem number 2. Okay, problem number 2, today's problem number 2. Okay, so once again the problem is the velocity of an electron with de Broglie's wavelength. De Broglie's wavelength lambda is equals to, that is 1 into 10 to the power 2 nanometers. It is given in nanometers. Okay, it is given in nanometers. Let us take options here. Okay, first option, second option, third option, and fourth option. So after solving that, we can find out which option is right. So that is, no need for options. Let us solve the problem. Why we required options? So this is, that is de Broglie's wavelength is given. We have to calculate velocity of the electron. Okay, calculate velocity of the electron. We have to find velocity of the electron. Find out, question mark, that is. Okay, what data is available? That much. All options are given in centimeters per second. Velocity is asking in centimeters per second. That's all. Velocity is asking in centimeters per second. Now let us take the basic fundamental formula. Lambda is equals to h by mv. Okay, that is the basic fundamental formula for us. Now we have to calculate velocity. Velocity is equals to h by m into lambda. That is the formula for us. That is equals to, okay. So options are given in centimeters per second, CGS units. So we should consider all the data in CGS units only. That is important. So therefore, okay, now Planck's constant value 6.625 into 10 to the power minus 27 erg seconds, okay, by mass of electron. Mass of the electron, is it the electron? Yes, it is electron only. So mass of electron is 9.1 into 10 to the power minus 28 grams, okay, into lambda. Wavelength is given, that is 1 into 10 to the power 2 nanometers. As we know that 1 nanometer is equals to 10 to the power minus 7 centimeters, okay, or 10 to the power minus 9 meters. So we required only CGS units into 10 to the power minus 7 centimeters. Now on solving this, now that is 6.625 into 10 to the power minus 27 by, that is 9.1 into, on solving this. So on solving this, how much we get? That is, okay, 0.728 into 10 to the power 6. Okay, so that is V, velocity, we are getting this much, R, that is equals to 7.28 into 10 to the power, 1 0 get reduced, 5, that is velocity in centimeters per second. Yes, okay, that is velocity of the electron. We calculate it like this. I repeat the problem again, listen. Okay, the velocity of an electron with de Broglie's wavelength. The de Broglie's wavelength is available. He is asking us to calculate velocity of the electron. Okay, then the basic formula, lambda is equals to h by mv, v is equals to h by m lambda. H is the Planck's constant. We should consider in ergs because the options are given in ergs only, that is CGS units only. So therefore all the data must be considered in CGS units only. So that is Planck's constant value, erg seconds, okay, and mass of the electron is in grams, and lambda must be in CGS, that is centimeters, because it is given in nanometers. As we know that 1 nanometer is equals to this many centimeters, okay, that is into 10 to the power minus 7 centimeters. Data collection and substitution is done. Then on simplification, on solving this, that is equals to, that is velocity is equals to 0.728 into 10 to the power 6, okay, R, that is centimeters per second only, centimeters per seconds, okay, by R. Next, when I am taking decimal, 1 digit more, so that is 7.28 into 10 to the power 5 centimeters per second, okay. I think the concept is clear to all of you. Okay, I read the question clearly, and the data only I am substituting here. The question already we have done. Okay, next problem number 3. Problem number 3. Next problem. Okay, next problem 3. Say at the beginning I am reading the problem numerical, because I am not writing that data, I am writing very short. Okay, the numerical is completely I am reading it. Okay, don't worry about it. Next, problem number 3. Problem number 3. Yes, that problem number 3 is, I'll read the problem number 3. That is, wavelength of electron with mass 9.1 into 10 to the power minus 31 kg. So here the mass of the electron is given in kg, okay, and with kinetic energy 3 into 10 to the power minus 25 joules, 3 into 10 to the power minus 25 joules, okay. I repeat the problem again. The wavelength of an electron with mass 9.1 into 10 to the power minus 31 kg and kinetic energy 3 into 10 to the power minus 25 joules, okay. What we have to find? Calculate wavelength of the electron, okay, wavelength of the electron, and all 4 options are given in nanometers. Be careful, options are in nanometers, so we should get the wavelength lambda in, we have to calculate in nanometers only, okay. Be careful. Problem number 3. So that is mass of the electron is given, that is equals to 9.1 into 10 to the power minus 31 kg. It is given, and kinetic energy of the electron is also available, that is equals to kinetic energy. How much it is given? Kinetic energy of the electron, it is 3 into 10 to the power minus 25. 3 into 10 to the power minus 25 joules it is given, okay. What we have to find? We have to calculate lambda. That is lambda is equals to question mark, that we have to find out, okay. Lambda we have to find out. Now the de Broglie's equation, that is relation between kinetic energy and de Broglie's wavelength, that is lambda is equals to, de Broglie's wavelength is equals to h by under root 2 ke into m, that is mass of the particle. This is the basic formula we required now, okay. Now we have to substitute the right data in the formula. Options are given in what I said, nanometers, yes. So mass of the electron is available, m is available, kinetic energy joules is available, and Planck's constant we should consider in joules only, okay. So that is lambda is equals to Planck's constant value 6.625 into 10 to the power minus 34 joule seconds by under root 2 into kinetic energy 3 into 10 to the power minus 25 joules, fine, and mass of the electron we know that how much, 9.1 into 10 to the power minus 31 kg, okay. So on solving this, lambda is equals to, okay, so that is 6.625 into 10 to the power minus 34 joule seconds by, on simplifying this root, okay, the value is 54.6 into 10 to the power minus 6, 54.6 into 10 to the power minus 56, okay. Yes. Now on simplifying this, lambda will be equal to, okay, on simplifying this lambda will be equal to 0.8966 into 10 to the power 6 minus 6, 10 to the power minus 6, then lambda is equals to, so when I am moving this decimal here, 3 digits move, that is it becomes 10 to the power minus 9, that is 896.6 into 10 to the power minus 9, okay. It is, you are getting in meters, okay, it is in meters, as we know that 1 nanometer is equals to 10 to the power minus 9 meters. So therefore it is equals to, lambda is equals to 896.6 nanometers. Done. Okay, once again I read the problem once again. the wavelength of an electron with mass 9.1 into 10 to the power minus 31 kg. Okay, when kinetic energy is this much, 3 into 10 to the power minus 25 joules, we have to calculate wavelength of the electron. Wavelength of the electron of mass and kinetic energy. Wavelength of the electron of mass this much and kinetic energy this much. He is asking you to calculate. Okay, formula and H. I said all the options are given in nanometers. Okay, we should remember that. So now when it is nanometers, okay, now H value, kinetic energy, H is, we know that H is a Planck's constant. Okay, substituted all the values. Okay, it is kinetic energy given into mass of the electron given in kg. Okay, I am solving this. So this is the value. So it is 896.6 into 10 to the power minus 9 meters, or it is nanometers. Problem. Is it clear to all of you? Just few seconds I will give. Just once again go through the problem slowly. Planck's constant value and under root 2 into kinetic energy is given 3 into 10 to the power minus 25. Yes, mass of the electron substituted. Okay, on solving this, so lambda is equals to 0.8966 into 10 to the power minus 6. Okay, 10 to the power minus 6 meters, or 896.6 into 10 to the power minus 9 meters, and this 10 to the power minus 9 meters is equals to 1 nanometer. That way it is 896.6 nanometers. Okay, problem. Is it clearly understood? Yes, the concept is clear in this. Okay, let us move to the next problem. Right. So now the problem number 4. Next, problem number 4. Yes, let us take up the problem number 4. Because whatever the problems we are doing in the e-learning program, so all these problems are very important for all your examinations, that is your board exams, that is IP exams, as well as your MCET exams, and the students, those who are very much interested in mains, and some students they might be interested in BITSAT examination also. So all these fundamental numericals are very, very important, because the basic fundamental is the common for everything. Okay, once the fundamental concepts are clear, then application part is different. So that is, the student may find the question in MCET paper, or they may find question in the mains paper or BITSAT paper, whatever it is. Once the fundamental base is clear, so then application depends upon the strength of the student. Okay, right. Now the next problem, let us see. The next problem is problem number 4. Yes, problem number 4. Yes. A cricket ball of 0.5 kg, that means half kg cricket ball, okay, 0.5 kg, is moving with velocity 100 meters per second. That cricket ball of mass 0.5 kg, it is moving with velocity 100 meters per second. Calculate the de Broglie's wavelength associated with the ball. Right. Let us take the data. Mass of the cricket ball, that is mass of cricket ball, how much? That is equals to 0.5 kg. Yes, and it is moving with velocity. How much velocity it is moving? It is moving with velocity, that is how much? 100 meters per second. 100 meters per second. It is moving 100 meters per second. Calculate the wavelength associated with the ball. Okay, calculate the wavelength associated with the ball, that is lambda we have to calculate. Okay, that is a problem. Okay, now let us see. All the options are given in meters only. All the options are given in meters, that is SI units. That means you are calculating the lambda in SI unit. That is, we should remember, in SI unit we have to find. That means in meters. Lambda will be in meters. Okay, that should not forget. Yes. Now lambda is equals to h by mv, basic formula we required. So then substitute the data in this. Okay, let us take that is equals to, so SI units, Planck's constant SI unit 6.625 into 10 to the power minus 34 joule second, yes, by mass of the cricket ball 0.5 kg, yes, done, into velocity of the cricket ball, it is moving 100 meters per second velocity. Okay, done. Okay, now the data is substituted, so h by mv, done. Then it is equals to, this is equals to, so that is 6.625, or let us take the, let us substitute the direct value. So that is equals to, the simplified value is equals to 0.1325 into 10 to the power minus 24, 10 to the power minus 24, sorry, 34, yes, it is 34, that is 10 to the power minus 34, okay, or it is equals to, when you take the decimal, 1.325 into 10 to the power minus 35, okay, it is in meters, lambda is in meters, because it is kg, okay, get cancelled and goes up, it becomes meters. Okay, this is the problem number 4. Once again, what is the problem? The mass of cricket ball is 0.5 kg, is moving with velocity 100 meters per second, moving with velocity 100 meters per second. Calculate the wavelength associated with the ball. Calculate wavelength associated with the ball. Okay, that is the question. I repeat the question. The mass of a cricket ball is 0.5 kg, moving with velocity 100 meters per second. Calculate the wavelength associated with the ball. Calculate wavelength associated with the ball in SI units, because options are given in SI units. Now, lambda is equals to h by mv. So, h is equals to Planck's constant we took in SI unit, joule seconds, and mass of the cricket ball already given kg, 0.5 kg, into velocity of the cricket ball is moving 100 meters per second, already given in SI unit, right? So all the data is substituted in SI unit only. On simplification, okay, on simplification, 0.1325 into 10 to the power minus 34, okay, or, okay, the option, that is 1.325 into 10 to the power minus 35 meters. Okay, so this is the numerical fourth part, that is fourth numerical based on de Broglie's concept. Okay, next let us work on another numerical number 5. Another numerical number 5. Numerical number 5. Right. Numerical number 5. Yes, I read the numerical. Yes. A microscope using stable photons is employed. A microscope using suitable photons is employed to locate an electron in an atom with a distance of 0.1 angstroms. What is the uncertainty involved in the measurement of its velocity? Okay, yes. You got it? No. Yes. See, in an atom, electron is revolving around the nucleus. Okay, understood. Electron is revolving around the nucleus. Okay, electron is revolving around the nucleus. Now, to identify that electron, so the being electron is microscopic particle, so we have to use microscope to identify the location of that electron. Okay, so now a microscope using suitable photon light, that means we have to identify, we have to focus certain photon light on that particular electron. Okay, suitable photons is employed to locate an electron in an atom within a distance of 0.1 angstroms, that is delta x is saying as 0.1 angstrom units. 0.1 angstrom units. Okay, what is uncertainty involved in the measurement of velocity? What is the uncertainty in the velocity that he is asking us to calculate? That is uncertainty in velocity we have to calculate. Okay, now delta v is equals to, let us substitute, delta v is equals to h by 4 pi m delta x. Okay, now the options for this problem is given in that is SI units, meters per second. Okay, so in meters per second we can, that is delta v in meters per second, that we have to calculate in this. Substitute 6.625 into 10 to the power minus 34 joule second by 4 into pi value 3.14 into mass of, it is electron only, yes, mass of the electron, that is we understood 9.1 into 10 to the power minus 31 kg. Okay, it is in kg, yes, into uncertainty in the velocity, that is uncertainty in the position 0.1, it is in angstroms, we must take in meters, so therefore into 10 to the power minus 10 meters. That should be very careful. That is this angstrom unit, that is 1 angstrom unit is equals to 10 to the power minus 8 centimeters, that is equals to 10 to the power minus 10 meters. Okay, we should consider this. So on solving this, delta v is equals to, okay, on solving this, the delta v is equals to okay, that is 0.5796 into 10 to the power 7 into 10 to the power 7. Okay, so there are delta v is equals to, let us make the decimal 5.796 into 10 to the power 10 get reduced 6, it is meters per second. 5.796 into 10 to the power 6 meters per second. Okay, so this is the data for the given problem. Okay, yes.